We've been able to demonstrate for the first time taking human cells and restoring function they had when they were younger.
Wow.
Everybody over a certain age is going to take these because, like, who wouldn't want to feel like you had the metabolism or immune system or whatever, or the muscle system of like a younger.
So you're injecting proteins, and
Yeah.
it would be an injection of proteins into the body that the cells absorb.
You're not going to be immortal because you could still get hit by a bus or something.
If you're 42 years old, are you going to stay 42 years old, or are you going to look like you're 32 years old?
And so we decided to kick off this company just a few years ago, and it's had some really exciting initial progress where we've been able to demonstrate for the first time taking human cells and restoring function they had when they were younger.
Wow.
Yeah.
Wow.
And there's some cool videos I can show you of just like, we have these like humanized mice model where we actually put human cells inside the mouse. And then like if you have an old mouse and a young mouse and you give them both a certain amount of alcohol, like the old mice take longer to sleep it off, it's kind of like people. And we've been able to like restore the liver of these older mice, and they wake up like the young mice with no hangover kind of thing.
Wow.
So again, getting this working in humans is like a big challenge. It's like definitely this could take another decade to like start to see drugs and therapies that humans could take, but it's early stage. It's an exciting company. It's like 35 people in South San Francisco. I put like 100 million of my money into it, committed to it, and we've raised some money from some really amazing people too. So anyway, that's an example of the kind of thing I've been working on.
What kind of things is that going to be able to solve?
Well, yeah. So imagine, we all kind of lose function in our bodies as we get older, right? Like the big things that, if you look at the biggest killers, it's like heart disease, cancer, diabetes. So a lot of medicine is targeting how do you treat that disease. But there's another theory, which is like maybe the root cause of all those things is that, our cells are just losing function as we get older. And so you're more susceptible to get these diseases. Like, I'll give you an example. So if you're like, let's say you're in your 20s or 30s and, you have some damage to your cells, like you drink too much, or you get sick, or like, and there's kind of like this insult or damage to your cells. Your cells have the ability to recover from that. When you get older, your cells don't really have the ability to respond as well to these kinds of threats, or like, it could be viruses, or, eating or drinking too much, or not getting enough sleep or whatever. They start to lose their function. And so instead of treating like the effects of these diseases, why don't we just try to restore the function your cells had when you were younger? And it might actually be like kind of a root cause of a lot of these diseases that manifest later in life. Like if you look at all those diseases I mentioned, they're basically highly correlated with age. The older you are, the more you're likely you are to get it, right? Like once in a while, you'll see a kid, like a young person who gets cancer or something, but it's very rare. It's almost all people later in life. And so it's kind of like what you might call like a root cause, or solving a meta problem. Like if you can solve this problem, it automatically like knocks out or minimizes the effect of a bunch of later diseases that you get in life. Like you might be familiar with the GLP-1s, like these Ozempic type drugs, and that's the first time we've seen a drug that's like $1 trillion drug where people, even healthy people, are taking it now because they just want to lose weight. I think that the exciting thing about these longevity drugs is that if these start to work, and again, it'll take like another 10 years or more to know for sure. If these start to work, like everybody over a certain age is going to take these because like who wouldn't want to feel like you had the metabolism or immune system or whatever, or the muscle system of like a younger person, right? Mm-hmm. That would just be more years of healthy life, to get stuff done. So anyway, I think we're on the cusp of potentially being able to make a breakthrough in this area. And it's high risk, but I think this is exactly what people should be doing. Like if you have some success in business, like try to push the frontier, right? Do something that's really challenging.
So how does it work? Is it like stem cell where they inject cells into you, or?
It's related to that. So yeah, the science behind it, I'll give you the high level version. So there's a guy, Shinya Yamanaka, who won the Nobel Prize, Japanese guy, in around 2006. And he showed you could take a skin cell and reprogram it into a stem cell, like you were saying. So, and through a bunch of work, he showed that if you basically put these 4 proteins in a cell, it kind of reverts back to an earlier state where it's a stem cell. And then it can redifferentiate into being a skin cell again, but with younger properties. So this was like a breakthrough in the field. He got a Nobel Prize for it. Subsequent to that, people have shown that you could turn a skin cell into a different kind of cell, like a neuron or a muscle cell. What we're trying to do is not change the type of the cell. We're trying to just change the functional age of the cell. Like if it starts as a skin cell, stay as a skin cell, but just be like a younger version of yourself. And so we're searching the vast space of different sets of proteins. They're called transcription factors, which basically turn on and off different genes in the cell. There's like a massive number of combinations of these that are potential. We've developed a high throughput screening system that can test like millions of hypotheses. And we're looking for interesting targets that come out. Like, to be honest, our understanding of the biology of it is not very good. We actually don't know why. Like, even though this guy won the Nobel Prize, we don't even really know how it works, like, and why it works, but he found something that did work. And so that's what we've done at this lab in South San Francisco. We've set up this high throughput screening system that's testing millions of different combinations of these, looking for novel sets of proteins you can put in these cells that change the state of it back to like a younger cell. And we know that.
So you're injecting proteins, and
yeah,
it would be an injection of proteins into the body that the cells absorb?
Yeah, and they're delivered via this thing called lipid nanoparticles. But yeah. It's basically a way to deliver proteins into these cells, and it causes them to turn on and off different genes.
Wow.
Yeah.
How far out do you think you are?
I mean, we're going to start clinical trials on our first program probably in the next year or two in humans. And that's where you have to go through FDA or different countries you can do it in. And then we have 2 or 3 other programs coming along. So I think within like 5 to 10 years, we'll hopefully have candidates ready for, potentially someone could actually go get it prescribed by their doctor in like, hopefully like less than 10 years. But, these are kinds of things that sometimes you need to try a lot of shots on goal to get something that works, right? And it can start to get expensive the later you are down doing these human trials. Like it costs something like $2 billion and takes about 10 years to get a drug to market. And that's with a lot of failures along the way. So, we're putting a lot of capital to see if we can come up with a breakthrough here.
So you're getting ready to be introduced to a whole other type of bureaucracy.
Yeah, the FDA. I mean, actually, inside the current FDA, they are trying to find ways to optimize this. Because, by the way, China is making very quick progress on how they run clinical trials. And there's a phenomenon happening where sometimes someone will publish a paper, like a research paper in the US, and then apply for a clinical trial. And before their clinical trial starts, there's already patients in China with that drug in their body, because they're kind of seeing all of our papers get published, and then they can run the trial faster. So there's people like in the current FDA that are trying to think about, I'll give you an example of how we could make it more efficient. So right now there's phase 1, 2, and 3 trials. The phase 1 trial is all about safety. Like, is this thing even safe to put in a human body? And phase 2 and 3 are about what they call efficacy, meaning does it even work? So first you check if it's safe. Second, does it work? One thing we could do is, like, if you pass phase 1 trial and it's safe, allow a doctor to prescribe it to patients while it's going through phase 2 and phase 3. I mean, if someone's at the end of their life, like they're going to die like in a month, and they have no other option, and we know it's safe, dude, allow them to take it, especially if a doctor.
We had something like that, right?
Like a right to try.
Yeah.
Those kind of things. But it hasn't gone far enough. That would be an example where we could really start to accelerate it. So I hope we get some of those things put through the FDA as well. Otherwise, like, these companies are going to start running clinical trials overseas just to get faster data back.
Yeah. I mean, I know you're in very early stages, but I'm just curious. I mean, how much, maybe you have a target, maybe not. Do you have any idea how much more life somebody could experience by taking something like that?
Yeah. So the initial drugs that'll come through, we hope they could add something like 5 to 10 years of life. But the real moonshot goal here is that if we get this working in one cell type, we can get it working in another cell type, and another one, and eventually you'll be able to take a cocktail of these that kind of help improve like a dozen cell types, especially your brain. Like, that's the holy grail kind of. And if that works, I mean, the goal is to get to like indefinite, right? Like, you're not going to be immortal because you could still get hit by a bus or something, or shot or something, right? But if you don't have something like a physical thing that takes you out, you should, in theory, I can't see any law of nature that's getting broken that would not allow you to become perpetually kind of renew, right? And there's all kinds of crazy implications of this downstream if this works. I mean, I'm kind of in purely hypothetical land here, right? I don't want to overstate this, but we might start to see these people that they look kind of young, but they look different. Like they're it's like the vampire movies or whatever. Like they look like they're in their 30s, but they kind of look different, like they're like 1,000 years old or something, right? So you get into all kinds of interesting sci-fi type analogies, and people come up with all these philosophical debates about, should we even want to live longer? Anyway, I think that curing disease, giving people the option just to live longer if they want to, these are all unequivocally good things. And so it's worth pushing on this frontier. But if it ultimately works, how it changes society could be quite profound.
Yeah, I mean, do you think it would it make an older person look younger, or would it kind of stunt aging? And you, like, if you're 42 years old, are you gonna stay 42 years old, or are you gonna look like you're 32 years old in a year or however long it takes to work?
Yeah, the answer is we don't know for sure. I mean, there are now examples of human cells that we've been able to restore. It's not just stop the aging. We've been actually able to restore function they had when they were younger. So in some sense, you can call it like reversing the aging, right? But, I'll give you an example. So like your skin, when we all start as like a single cell, like a fertilized egg, right? And we're dividing, and our skin and bones and like brain, everything kind of develops. Like in our skin, we have this thing called the extracellular matrix, which is kind of like this protein structure. It's not the cells themselves, but it's kind of like, you probably heard about collagen and these different, so it kind of gives your skin like that flexibility and springiness. And over time, that the ECM, the extracellular matrix, kind of can deteriorate, right? So this is like a big open question. If we restore your skin cells to be like they were when they were 20, are they actually going to go in there and maintain and repair the extracellular matrix so your skin stays like really springy? Or are they just going to be like aged, are they just going to be young cells but on an aging extracellular matrix? We don't really know. We got to go run these experiments. Another example would be like, people who they have like scarring on their liver. It's called like fibrosis, right? If you damage your liver, it develops this kind of like scar tissue. And one of the experiments we've kind of been running recently is like if you reprogram your liver cells to back when they were younger, maybe your liver cells are young, but it's the scar tissue is still there. This is still too early to say, but like some of the data we've been seeing indicates that the young cells can actually like repair or disintegrate the scar tissue.
Wow.
So we don't know yet, but like there's a possibility that if we actually are able to successfully restore these cells back to the younger state, that they'll just like kind of maintain and restore.
No matter where you're watching Sean Ryan Show from, if you get anything out of this, please like, comment, subscribe, and most importantly, share this everywhere you possibly can. And if you're feeling extra generous, please leave us a review on Apple and Spotify podcasts.